All right. Well, here's a few news stories that I thought were interesting. This one here is one of the best graphs. This comes from, I think, the Financial Times or something. But as you see, the U.S. is now up here with the largest number of reported cases and the fastest rate of growth of any nation on Earth, if you count the days since the 100th case, which would make sense. I made a separate chart, which I haven't got right here, of just what's been happening in San Francisco, and it made me feel that things may have begun to peak just in California, because we've had everyone staying at home for about almost 2 weeks now, and logically a couple of weeks, 2 to 3 weeks after everyone's staying at home, we ought to see it go down, but we haven't seen that yet. So the shelter-in-place order has been extended to May 1. So I think the college has not officially said when they would reopen the buildings, but I think it's pretty clear we're not going to reopen the buildings at all again this semester. They may have officially said that too by now, but I think it's extremely clear that we're going to be sheltering at home for a long time yet. And so the classes will proceed only online. WireGuard is a VPN that is considered more advanced and newer than the others. I've heard a lot about it over the last couple of years, and now they're building it a Linux kernel, so I might take a look at it. I think I tried it a couple of years ago and it wasn't ready enough, but I might try it again. I've written in the web design class a project setting up a VPN using shadow socks, which is a sort of new one I learned about in China, and this is another new one. And it claims that it's easy to set up and now supported to some extent in all operating systems. There is a version, although a beta, for all the operating systems, so it might be worth trying it as well. There is so much COVID-19 misinformation that Snopes has been overwhelmed. Their volunteers cannot detect the fake stuff fast enough, so they're having to prioritize stuff and scale back their fact checking. This is a very, very old problem of fake medical information. It's like the fake diet information. It's always a huge and productive scam, and it's going on a lot now. So I always go to B-Sides and DefCon and Black Hat in Vegas, but I really don't think any of them are going to happen this year, but none of them have officially canceled yet. DefCon said on June 1, they will have an announcement of whether they're going to cancel it or not. But B-Sides has already begun to talk about this, and they have a page. They haven't yet announced that they're canceling, but they are saying that on June 5, they'll make their final decision. I think these well-established conventions are worried about canceling because they don't want to alienate their audience, and it's really important to people, but I think there's no chance in the world. I understand the economic pressure, especially since Vegas exists entirely for large gatherings of people physically. They will have a strong incentive to try to allow that, but I just do not understand how anybody can have a large gathering of people physically in America this summer. I think it will never be possible. I think the states are now closing their borders, the airplanes aren't flying, and everybody's afraid, and I just don't think it can possibly be done. Probably not for the next year or more, not until there's actually a functioning vaccine, I would think. This is very interesting. I learned about today. AnyRun is some kind of automatic malware hunting service, and this will let you automatically run something in a sandbox on their server and give you a report of it. So that looks like fun, and there's even a free tier. So hopefully I can make some projects using this sandbox, and we'll see how it compares to other ones. VirusTotal sometimes gives you some sandbox reports, so that's another one to compare to it. Another thing I saw today, which looks very good, is Google's Python class. It looks very nice, covering all the important stuff, free from Google with exercises and such. So I'll take a look at this, and if anybody wants to work through this, I'm sure it's worth extra credit. Python is very important to know, and a good free class to learn it is very welcome. This firm Votes has been in the news quite a while. They've had some serious security flaws. They are one of the people pushing online voting. They're trying to convince people that you can use this app on your phone to vote in elections, and that somehow it will be secure enough to trust. And all the reputable security experts I know say that online voting will never be secure enough. There's no way to do it at all. But these people have managed to convince a few small elections to actually use it. And they, in order to improve their security posture, they had a HackerOne bug bounty program, but HackerOne has now thrown them out. They are the first company ever to be thrown out of HackerOne, but they have had appallingly bad behavior. They lied about flaws and kicked people out and so on and denied things and such. So it's they certainly have had a very bad reputation. I thought they were doing a little better lately, but anyway, they have somehow managed to get kicked out of HackerOne, which is not a good look. This is a real step forward in the maturity of companies in security when they have to. In the past, maybe 20 years ago, companies would just pretend they had no security flaws and just lie about everything and get away with it. Then they had to begin, like Microsoft, admitting they have flaws and putting out regular updates. And then I think in the modern world, increasingly, you're expected not only to do that, but also to participate with the white hat hacker community and allow people to submit bugs and have some kind of responsible disclosure policy where there's some way they can report something and you won't lock them in jail and maybe even give them some kind of thanks or money or something. And I think especially in something that is very, very security sensitive, like voting, where there is a very large feeling that your app is probably not secure enough, you really have to go the extra mile and demonstrate real dedication to security. And these people appear to be failing that test still. They have been failing it since they started. So as New Jersey sent the police to stop everybody with New York's license plate and to knock on everybody's door and find out who'd been coming from New York in the belief that they can prevent the coronavirus in New Jersey by keeping people from New York out. And many states are now closing the borders. I think Kentucky just closed their border today. So nobody is telling people they can't leave the state. Among other things, this is almost certainly unconstitutional. This is a fundamental right in the United States Constitution that you're allowed to travel within the country without a passport or anything. But then they had a bunch of vigilantes in Maine that tried to block the road with a tree to stop people from coming in and tried to force people who they thought had just come in from another state to quarantine for 2 weeks. So, as the panic over coronavirus gets bigger and bigger, we have more and more of this madness going on. Of course, as usual, fueled by Trump, he said he was going to quarantine New York City, and then they said that would be illegal. But it is, people are getting very, very afraid, and they're starting to do very many crazy things about it. Again, not helped by the government. Singapore and Hong Kong, and as far as I can tell, mainland China and many other Asian nations have just accepted everybody wearing masks a lot of the time. And I know in Hong Kong, they attribute their success at having very few cases to the masks. And in America, the Center for Disease Control told people not to wear masks. And this seems to be absolutely false. I've read many convincing articles from other nations saying this is garbage. Wearing a mask, even just a handkerchief over your face, even a homemade makeshift one, does, of course, make you a lot safer, because even though the cloth is not so fine as to stop particles of virus, it is enough to stop particles of spit. And that's what you're trying to stop. Somebody has sneezed or something, and you're just trying to stop those droplets of water from coming in with your breathing. And even a makeshift mask is really quite effective. So I started wearing a mask in public. I think everybody should, because you want the people that are sick to wear a mask, and you don't want them to feel like they're being marked as like a bad person by wearing a mask. So just everybody should wear a mask in public, and we would all be a lot safer. So even if you just have a makeshift one made out of a t-shirt or a handkerchief or something, it's a good thing to do, although the Center for Disease Control has come out again and said we absolutely do not recommend it. The American medical community is famous for being very slow to adapt and conservative, and often not saying things they should say until much later. Anyway, so let's get on to the official stuff for this class. So we are here. I've updated the schedule for this class, although I haven't updated it for my other classes yet. I'll probably do that tomorrow. So we lost 2 weeks to this coronavirus. I tried to have a class last week, but decided against it because people were too distracted by the chaos, which I understand. And last week was the official spring break. So now we're back on track, and we'll just start with chapter 4 here. And next week you've got a paper due, those of you that haven't turned in your paper yet. And then there's another presentation coming and another paper later in the class. So this is basically the Net Plus review. Remember I said before at the beginning of the class that Security Plus is A+, Net Plus, and Security Plus, plus about as much management. So these are things you've hopefully already learned in other classes. But if not, regardless, we'll go over it here as either a review or maybe it's the first time you've seen it. So network architecture and design. Here's some fundamental concepts. If you have a communication channel between two devices, the simplest one is a simplex channel that goes only one way, like an FM radio. They can broadcast information from the station that comes to you, but you cannot respond at all. Then there's half duplex, like a walkie-talkie, where you can send or receive, but you can only do one of those things at a time. So you have to let go of the button to listen. But most everything now is full duplex, just like real talking through the air, where two people can both talk and listen at the same time, like a telephone. All right, baseband is where you have a communication channel that is entirely dedicated to one signal, like Ethernet. You have an Ethernet cable, and there's only one computer on the end of that cable, and all the traffic, even if it's a switch connected to many computers at one end, the communication from one end to the other of that cable is allowed to use all the frequency available on that cable. Broadband is the alternative, like FM radio, where you have one communication channel shared by many stations, and they each get only a certain bandwidth, so many of them can communicate at the same time. Analog transmissions are like FM radio again, where you have a signal, and the signal just gets larger when you want the noise to be louder and softer when you want it to be quieter for an audio signal, and you just translate that to an amplifier, so that if there's any noise in the signal, it just causes distortion and there's no clear way to remove it. Digital is the step forward, where instead you just send a series of zeros and ones, and now you can have error correction, and you can repeat signals that transmissions that get lost until you get 100% perfect transmission, where it passes a integrity check at the other end. And so it is possible to have essentially perfect transmission from one end to the other, which is not possible with an analog system. So local area networks are within a building, and then you have various ones like MAN and such, but WAN is the main one people use, covering anything large like the internet. Another one used sometimes these days is PAN, your personal area network, between the devices you carry, typically Bluetooth, so your phone can talk to your headset and so on. The internet is the global collection of all networks running the TCP/IP suite of protocols. This became the standard because of Unix and C. In the early days, there were mainframe computers, and they each had their own branded operating system. And C was written as the universal language to make it possible to run Unix, which was the universal operating system. And then TCP/IP was the way to make those Unix servers talk to each other. And all other computers eventually obeyed it. And that's now the universal language is TCP/IP for communication over the internet. An intranet is a privately owned network using TCP/IP. A more modern term for a similar idea is a private cloud. And there are extranets too that connect to a limited number of people, like business partners. Circuit switching is the old system where you have one physical wire dedicated for one conversation, but almost everything is now packet switched, where multiple signals go down the same line, packets just alternate from one to another, and many different kinds of traffic are sharing the same line. Therefore, you have a problem. You might have time-sensitive traffic, like live voice over IP, like what I'm using right now. I'm talking into a microphone that is sending packets to people. And if those packets are delayed by even as much as 50 milliseconds, it greatly degrades the quality of the voice. So that's not acceptable. Whereas you have other traffic like email and web pages that could easily be delayed by 50 milliseconds and it wouldn't matter. So you use quality of service to mark which traffic is high priority and which traffic is lower priority, and can wait until there's a gap in the high priority packets. This is all done with layers. Layering is the fundamental way to make it easier to make a suite of devices and protocols that interoperate by restricting what they do. So each layer performs a certain function, and you can buy or build devices at one layer and a different brand at another layer and combine them. So you have network models. The main ones are the OSI model and the TCP/IP model. There are also network stacks, the protocol suites, which is all the various communication systems you need to get the jobs done, and TCP/IP is the most common one there. So here's the OSI model. From the bottom, physical data link network, transport, session, presentation, and application. Please do not throw sausage pizza away is the common mnemonic. You certainly have to know this, although it is somewhat artificial. The bottom 4 layers are really real, and you have different pieces of hardware taking track of these. Layers 1, 2, 3, and 4. 5, 6, and 7 are usually all combined in a single application like your browser, and the difference between them is not really very important. But 1, 2, 3, and 4 are very important, and we'll spend most of our time focusing on them. Layer 1 is the physical connection. So this is how bits are transmitted from one device to another down things like Ethernet cables or radio signals. And this is where you have a network cable, a hub, repeater, and such devices that just make a physical connection from one device to another. Layer 2 is the data link. Now you're going to have an Ethernet card and a switch and a bridge. These are devices which layer 2 traffic has an address. Layer 1 traffic is just physically moving down a wire, an electrical signal that just transmits. Layer 2 is where you have an address, and here it's a MAC address to move frames. So technically there are 2 sublayers, media access control and logical link control. Layer 3 is the network layer. So this is where you take traffic and put it in packets and move it over a large geographical distance to find the geographical location of your destination computer. So this is what performs routing, and you have routers, and this is what the internet is a series of routers that can take traffic from one physical location and route it to another physical location. And the transport layer is where you have TCP and UDP. There are other protocols, but those are the most common, and they have port numbers so that when you have given your device your data, broken it up into segments, given them, delivered them with MAC address on your local area network, and then by IP address over the global internet. So you now make it to the physical device you're trying to talk to. The transport layer tells you which process you're trying to talk to on that device. That's what the port number is for. So your server might be running email and HTTP and HTTPS and other protocols, and the port number is used to determine which of those you're going to communicate with. TCP is reliable. All the packets have a segment number, so they can be reassembled in order at the other end, and they have a flow control system so that if a packet is not delivered, that failure to deliver is detected and the packet is resent, so that under normal conditions, TCP will eventually deliver 100% of the data 100% intact. UDP is just sends packets with a best effort of delivery. There is no way to detect whether they really are received or not, and so it is considered unreliable. On the modern internet, data packet loss is less than 1%, so typically things sent over UDP do in fact arrive intact, but it is not certain that they do, whereas with TCP, it is much more certain. Then you have the session layer, where you have things like keeping track of whether you've logged in or not, which is a higher level, more abstract concept. And the presentation layer, which will convert data from a computer readable form into a more human readable form, like converting ASCII into readable characters and decompressing compressed data. And then the application layer is what presents it to the user. This is what most people live their whole life at the application layer, looking at a web browser, an email client or something. And when you hit send on an email, it goes down through all those layers, sent to the other end down the physical layer, and back up all the layers to the person at the other end. But normal users don't really know or care how that works. So I got some Cahoots about that stuff. Let me find my Cahoots. Here they are. And this ought to be 4A. Looks good. Teach, I guess. Looks like they're adding more features to Kahoot. All right. All right. And all right, I only see 6 people, so I'll just give it a few seconds, but I don't think we can possibly get over 5. Five more seconds. All right. All right. What OSI layer has MAC addresses? All right, good. Layer 2. All right, where are the hubs? Hubs are layer 1. They just connect wires together. They're stupid and do not know anything about addresses. All right. What kind of transmission goes through Ethernet? Okay, that is baseband, because 100% of the bandwidth is available for one signal. All right. What layer includes network file shares? That's 4 or higher. I think in these slides I put it in 5, but like I say, 5, 6, and 7 pretty much blur together in practice, and distinguishing between them is not usually that important. All right, so we have winners, Vu. All right. No name will have to come out of the closet if they want their points. And aha, I see a chat message, Derona. You'll also have to tell me who they are if they want their points. Let's see what this chat message says. Aha, okay, good. Oh, tell me who they are. Okay, Derona is someone I probably should have guessed, Ed. And this is Artem, okay. Good. All right, so let's go back to the slides. I said, wait a minute, I wanted to leave. Okay, there we are. All right, so hit these buttons. Theoretically, it will get big. There we go. All right, so here's how it compares to the TCP IP model, where network access combines data link and physical, network changes its name to internet, transport is the same, and the higher 3 layers are just called application. That is probably a little closer to the way real hardware is. Then the TCP IP is a little bit more theoretical. Anyway, so network access layer combines those 2 layers and has the MAC addresses. The internet layer is the same thing as the network layer, using IP addresses on either IP version 4 or IP version 6 to route packets to the right physical location. And the transport layer is TCP and UDP, typically where you have port numbers. Those are the most common layers there. And the higher layers are all just called the application layer that takes the data that came in from the network and processes it as necessary to turn it into something that you can present to the human user. This is all done with encapsulation. So you have, this is like putting a letter in an envelope and addressing it. Every packet has 3 addresses, which at first sounds ridiculous, but you get used to it. And so as you start at the top and do something like click send in an email client, your data is then broken up into segments, which are the right size, and at layer 4. It's put in a segment and given a layer 4 address, which is a port number. Then that is encapsulated at layer 3 in a packet and given an IP address. And that is encapsulated in layer 2 in a frame and given a MAC address, which is then sent over the wire. So it's like putting an envelope inside a bigger envelope inside a box. And that's the way all traffic is sent. So here's a mnemonic for that, SPF10, segment packet frame, and 1 and 0 for bits if you like. I think that's referring to a sun protection factor from a suntan lotion. Anyway, so you have to decapsulate it at the other end. At the other end of an Ethernet cable, you get raw bits, and you then have to convert the bits into a frame, remove the MAC address and turn them into a packet, remove the IP address header and turn them into a segment, remove the TCP header and then you have data that you pass on to the correct application. All right. So MAC addresses are 48 bits long. The MAC address of a network card is burned in at the factory and typically cannot be changed thereafter, although you can change it in software of the operating system running it, and that is commonly done. All right. In IP version 6, there is one early version of addresses actually included the MAC address in the IP address, but that was realized to be a privacy risk and is not used that much anymore. Most people use privacy enhanced versions of IPv6 addressing these days. IP version 4 is the most commonly used system with 32-bit addresses written as 4 base 10 numbers like this, 192.168.0.1. And the header looks like this. The version number is always 4 for IP version 4. And then you've got things here like time to live, which is how many hops it can make before it gets thrown away, and source address and destination address, and a few other things here. That's the IPv4 header. There is a part of the header that can actually perform fragmentation, which is a sort of unwise thing that was invented in IP version 4. Never had much practical use, except at a time long ago when there were actually token ring networks interacting with Ethernet networks. That's essentially obsolete now. And the only thing it does is give a way for hackers to sneak data through firewalls, because you can fragment packets up into a lot of small packets, so each one packet doesn't have very much of the information. All right, there's a thing called the don't fragment bit and so on in there, but this I think is not used for any valuable purpose very much these days. The IPv6 header is much simpler. It actually has fewer fields. The addresses are much bigger because the addresses are 4 times longer. They're 128 bits instead of 32 bits, but they got rid of a lot of the unnecessary complexity of IP version 4. So the right 64 bits are used to construct the host portion of the address. You see here in INET 6 FE80 : AEBC 32FF, FEC3, and so on. You can look at the Ethernet address. Let me just make this so now I can point to it. If you look up here at Ethernet address, ACBC32C3, you'll see that down here. Here's the C3, 9E, B3. Some of it anyway is clearly present there. So let me see, I see a chat message coming in. Isn't that backwards? Okay, he said never mind. Okay, good. Anyway, so the, all right, so anyway, the point is, yes, the AC changed to BC, ACBC, 32, all right, a lot of it is here. It looks like it's a little bit garbled, but anyway, a lot of the Ethernet address ends up down here. I think the first 3 bytes end up here, then there's always an FFFE in the middle, then the last 3 bytes here. That's the old system where it actually put your MAC address in the IPv6 address, which is considered an unwise way to do it these days. But IPv6 turned out to make some trouble for security because a lot of people had IPv6 turned on automatically by the operating systems on their computer, but the network devices and the firewalls and such were not ready for it. So there was a time when you could sneak traffic past network defense devices by hiding on IP version 6. I think that is less successful now. I think a lot of people have now gotten used to IP version 6 and upgraded to either prevent it entirely if you don't want to use it, or if you are going to use it, correctly filter it. You can disable it at the end by just unchecking this box in the properties of your network card, and then your network card will no longer send or receive IP version 6. Classful networks are the original system. Well, the original system was Class A only. Then they upgraded, I think, in the 80s to classful networks, described here with Class A, B, and C networks. And that was used until 1993 to extend the range of the IP version 4 address space. And so Class A was /8. This is a classless internet domain routing. This is what we're using now, where you can have all sorts of network sizes. /8 is the one with the number after the slash is the number of bits used for the network portion of an address. So Class A has the first number, like 147, would be determining the network, and all the rest would be used for hosts. This 147 is a Class B network, and that means 147 and 144 are the network portions, 96.0 are the host portions. So you have 65,000 and change possible devices on your subnet. Anyway, The private addresses, everybody needs to know these. 10.anything is private, 172.16 to 172.31, and 192.168. And this is what most people use. If they're behind network address translation, you have a private address, which cannot be used on the internet. If you send packets to internet routers with these addresses, they will just be thrown away, but you can use them for local addressing. They have to be translated to a real public address, though, to get anywhere on the internet. So let's go to 4B. All right. All right. All right, I bet we're going to have at least one more. Maybe not. I'll give it another 5 seconds. Ah, there comes somebody. Okay, good. All right. So where are the segments in the OSI model? There are layer 4, TCP segments. All right, which addresses are 48 bits long? The MAC address, all right. Okay, what class is that address in? 208.67. That's a class C. The first 128 are class A, then 64 are class B, then 32 are class C. So high numbers like that, like 208, put it in class C. All right, and which addresses are 32 bits long? IP version 4. All right, so no name is ones again, good. Ampero, okay. The real name, and Vu, good. So I have names for everybody this time. All right, good. Let's do one more of these then. All right, so there's network address translation. As I mentioned before, typically done with port address translation. That's the most common kind you've seen, so that you can have one public IP address shared by many devices. This is what pretty much everybody has in their home. There are other techniques like static NAT, pool NAT, where you have a one-to-one mapping of local addresses to public addresses, but those are rarely used. That's not the case most people want. So this is the way NAT looks. You have a device at the top going to the internet that has 2 network cards, one going to the public address going to the internet, and then a private address. Let me just shrink this down so I can hopefully point around with my mouse, and I think the video will pick it up. So here's the local default gateway, 192.168.1.1. And what I have here is IP address, subnet mask, and default gateway. This has a real public address as its gateway, so it will send traffic off to the internet. All the other devices send traffic to the router, which then forwards it to the internet. And all your local devices have to have addresses in the same subnet, but with different unique addresses. So this is a class C address with 255.255.255.0 network subnet mask, which means that all the devices must have addresses starting with 192.168.1. and then they just need different addresses here. So the router in this case gets a 1, and the computers get 101, 102, and 103. That's what you typically have in a home network. ARP is used because when you first try to reach a computer on the network, like the default gateway, you don't know its MAC address, and you cannot send any data on an Ethernet network without knowing the MAC address of the device you're talking to. So you have to find it. So you send out an ARP request saying, who has this address? Tell me. And that is a broadcast address that goes to everybody you can reach. And then somebody will tell you, I am that, and give you the MAC address of it. And there's always a ton of these ARP packets flying around every network as devices are trying to talk to something, and any device that has not spoken to that other device in about 2 minutes has forgotten where it is, and it has to ask where it is. Unfortunately, ARP packets have no encryption, no authentication, no integrity control, and you can very easily forge them on networks, and that's how you do poison ARP protocols. If nobody is actively attacking it, though, it works fine, and that's normally the case. All right, so here's ARP request and reply. I ask, where is the gateway? And it tells me where it is. But as I said, you can have an attacker who lies and claims to be the gateway when they aren't. So anybody on a public broadcast network can intercept traffic and place themselves in the middle, and that's involved in an awful lot of hacking attacks on a local area network. The only reason why this is not a bigger problem in practice is you have to be physically close to the client. You can't attack somebody over the internet this way. You have to be on their layer 2. And you typically just secure that with old-fashioned techniques like hopefully knowing who's inside your building. Unicast traffic is one sender sending data to one receiver. This is the most common way. Multicast lets one sender send to many receivers, and it's not used very much anymore except by routing protocols to dynamic routing. Broadcast traffic let you send a packet of traffic to every device on your network, and that is very common in the case of ARP. You send these ARP requests, and DHCP, when you first boot up your computer, you send out broadcast traffic on the LAN. There used to be something called directed broadcast, where you could send broadcast traffic over the internet to a distant network and then talk to every device in that network, but that turned out to be a security risk because of the Smurf attack, and that's no longer allowed on the internet. You can have a promiscuous NIC, which most network cards can be adjusted to ignore the MAC address of incoming traffic and pass all traffic on to higher layers, whether it was really addressed to you or not, which is something that has no purpose for normal networking, but a person might use it to diagnose a problem, or if you're an attacker, to sniff on traffic that you shouldn't be able to see. So there are various systems. Microsoft's made a few that will try to detect if anybody is using promiscuous mode and then flag that as a security violation. All right. If you're using a switched network, then the switches don't deliver any traffic to you except what should be coming to you, and therefore putting your NIC in promiscuous mode doesn't matter so much. But wireless networks cannot be switched. Physically, the traffic goes to everything in the room, so that's where you mostly see promiscuous mode used these days. TCP header looks like this. You have a source port and a destination port. They're 16 bits long each, then a sequence and acknowledgement number that are used to order the packets, and then flags like SYN and ACK and urgent and FIN, and other things here, but those are the most important ones. So the first 1024 ports are called well-known ports, and you cannot listen on these ports unless you have root privileges. They're reserved for important protocols like HTTP and HTTPS. All the higher number ports are supposed to be used by less important things like chat clients and temporary connections that you won't use for long. There used to be a distinction between the ones going up to 49,000 and the ones above 49,000, but Microsoft ignored that and sort of blurred them all together when they made Windows XP. So a socket is what you see here. You have a local address and a local port number and a remote address and a remote port number, and those 4 numbers together are called a socket, and they create a virtual connection between one process on your machine and one process on the server, and now it's as if you had your own physical wire connecting those two. You can send and receive traffic from your process to that process, and although it is going down a shared channel and it is not protected from eavesdropping or interference by other people. If nobody is attacking it, data will be transmitted between those two processes as if they had their own cable. So you have states of a socket. Listening means you are running a process that's listening, waiting for a SYN. Established means you completed the TCP handshake of SYN, SYN-ACK, ACK, and now you're ready for two-way communication. So the flags are here in TCP. You initiate a connection with SYN, you acknowledge it with ACK, you terminate it with FIN normally, and if you just cancel it in the middle of a transmission, that's a reset. And the others aren't used that often, but there are a few others. So there's the basic TCP handshake that you use to establish a connection with a server. And UDP has none of that. No flags, no handshake, no nothing. All it has is a port, source port, destination port, and then you just send the data. And you don't even know if it got there. There is no acknowledgement. You don't know if the other end is up and listening or not. That's it. This is commonly used by things like a security camera. It's in a parking lot spitting out the data, and it just wants to continuously send out the data, and it doesn't know or care whether a device is listening right now. All right, we'll do 4C. That's as far as we're going to go today. Let's find it. 4C is here. Okay. I see another comment here. I always thought a socket was just one pair. No, that's not. A socket is all four. Yeah, that's an important issue. Well, I don't know how important it is, but that's the way it is. All right, I bet that's it. Let's see if any new people have come. No, in fact, one has already left, so 5 it is. All right. So what kind of transmission uses that address? That's the local broadcast address. That'll send to every device you can reach. All right. What UDP flag initiates a connection? Okay, none of them. There is no connection in UDP. There is no flags. There's no handshake. Doesn't do any of that. You just send out the data like me. You're talking in a room and you don't really know if anybody's receiving it. All right, what TCP flag initiates a connection? That's SYN. SYN is how you start it, okay? And what ports require administrative privileges to listen? 1 to 1023. I sometimes see people say 0 to 1023. I think there might be something special about port 0. But anyway, that's it. These are the low-numbered ports where you must have administrative privileges to listen on them. VU, all right, the winner. And Brian E. Stark will have to tell me who they are. And Ampero, good, all right. So, good. All right. So I'm going to stop the recording and I'll leave this